All right, guys. So we're going to look at a related rates problem, and this one's pretty simple and straightforward. So it'll be really good for you to be able to grasp this one in order to do some of the more complicated ones. The basics of related rates is that you're actually using implicit derivation to solve for like a rate, or that dr over dt, or that dv over dt, or whatever that rate point is. So let's look at this example. If a spherical balloon is being filled with air at a rate of 20 cubic feet per minute, how fast is the radius changing when the radius is 2 feet? So keywords that make us know that we're going to be doing some sort is that we're asking us for a rate, or how fast it's changing. How fast is the radius changing? So what we're looking for is dr over dt, or the rate of the radius in regards to time. So that is our unknown. So I always set up what I know and what I'm looking for. So I know that dv over dt is 20 cubic feet per minute. I know that the radius is 2. I know that I'm looking for dr over dt. And I know that the balloon is a sphere. So I also know that that volume formula is going to be 4/3 pi r cubed. So let's get this going. I know I'm going to be derivating this expression, so I'm going to pull this up here. A lot of times we have to get everything in terms of one variable, but it already is. So for example, if there was something that we're talking about a height, you would need to change that h value into be in terms of r. But let's get this done. I know that dv over dt equals 4/3 pi times 3r squared dr over dt. These 3's cancel. I know that dv over dt is 20. We have pi times, 4 pi times the radius, which is 2 squared dr over dt. Now I'm looking for that dr over dt, so I need to isolate that variable. We get dr over dt equals 20 divided by 16 pi. And that is going to be feet per minute, because the radius is a single dimension, so we have just feet per minute. And I can simplify this even further. We can leave it there. We can also write this 5/4 pi feet per minute.